This is the work for exercise 1 with the non-inverting amplifier. So just using current rules and op-amp rules. So 0.1 is equal to 0.2 in terms of voltage, and 0.3 is just V out. 1 and 2 equal VI, and then just sum of currents in is equal to 0. Solving for V out and then dividing V out by V in to get gain is equal to this, R2 times quantity 1R2 plus 1R1. This is my Arduino code for exercise 2, which just reads in the V in, V neg, V out, and V plus values, and then assigns them and then prints them to the serial. This is my processing code for exercise 2 and the entire lab, with just the same as from lab 5 with changes to incorporate the new voltages and a new legend.
This is my circuit for exercise 1 with all the cables jumped in the way the lab states.
This is my output from the Arduino for exercise 2, and currently, so this is changing the V in up to 5 volts. As you can see, the green and blue, which are V plus and V out, they follow V yellow, or V neg and V out. And then as you go down, it continues to follow. It doesn't really follow this top 5 volts, which is interesting. And then as you go down, there comes a point where it doesn't follow, which I expect it to be about 2.5 volts, but here it seems to be about like 2.2 volts. And as that happens, that's because the op amp is between 0 to 5 volts, so ground, quote unquote, would technically be 2.5 volts instead of the normal 0 volts. As you see, it comes back up and follows again. And as it plateaus at this voltage of like 2.1 volt or something, green follows blue instead of following yellow and white, which are V in and V plus. This occurs because the V neg is jumped to V out, so it'll just follow that at that value. This is my circuit for exercise 3, the inverting amplifier, with all the resistors, R2, R1 here, 10,000 and 1,000, and then the voltage divider to create the input.
It's the processing window output for the exercise 3, the inverting amplifier, which the gain should be negative 10, which means this V out, blue line, should be equal to negative times 10 of the white line. But as you can see, it only really works at values close to 2.5 volts. This is because the range of the V in is plus or minus 2.5 volts from 5 to 0 with a medium of 2.5. And if the V in is too great, 10 times V in is going to be out of the bounds. And that becomes very quickly like 0.25 volts. So as you can see, values close to 2.5 volts for white. Yellow represents 2.5 volts straight across. The blue V out is what I assume to be 10 times V in. And then at a certain point it just plateaus, which is basically the out of bounds for the thing. And you can see it's not as represented on either side. There's more on the positive of 2.5 than the negative, and that's probably because the actual middle isn't 2.5 volts, it's probably like something like 3. This is the integrating amplifier, using the same current rules as when I did the non-inverting amplifier. V in, V out, and then this minus is equal to plus, which is ground. So sum of currents, V in over R plus C dVO dt equals 0, this being the current through a capacitor. dVO dt equals negative V in over RC. VO equals negative 1 over RC, integral V in dt plus some base V in. This is basically the integrating the V in over the change in time to find the V out, which is why it's an integrating amplifier. Processing output for the integrator circuit output amplifier. So as you can see, when I decrease the V in, the white bar, to 0, the green V out follows it at a exponential, which is expected because it's on the capacitor. And then when increasing, when the V out does not actually equal V in, or when the V plus, or V neg doesn't actually equal V in, the V out is integrating that difference here, which is seen by the adding, it's integrating the opposite of the difference over time, and then once they become equal, it flatlines again, which is supported by the theory that is shown in the solving for the gain in the circuit. The gain here is the integral of the difference, basically.